It is the night of August 12th, 1944, somewhere in the middle of the English Channel, and a vessel that looks like nothing else afloat is dragging a 200-ton steel drum through the darkness. There is no moon to speak of, and the crew have been ordered to keep noise to an absolute minimum. Beneath the water, unseen and unheard, a length of flexible pipe no thicker than a man's thigh is unspooling from the drum and settling onto the seabed, meter by meter, mile by mile. Nobody on the German side of the water has the faintest idea it exists. There are no explosions here, no dogfights, no burning wreckage lit up against the sky. Just a slow, patient, almost domestic act of engineering, carried out under the noses of an enemy who is still searching the coastline for signs of an invasion fleet that has already landed. This is Pluto, the pipeline under the ocean, and by the time it is finished it will have done something no army in history had managed before. It will have fed a war machine across a sea, invisibly, continuously, for months on end. To understand why a handful of engineers were laying pipe across the channel floor in the dead of night, you first have to understand the problem that was eating away at Allied planners long before a single soldier set foot on the Normandy beaches. An army that moves does not run on courage or steel alone. It runs on fuel, tanks, lorries, aircraft, generators, field kitchens, radios. Every single piece of the machine that would need to punch through occupied France and on into Germany itself was thirsty for petrol, and thirsty in quantities that beggared belief. Planners working on Operation Overlord calculated that the invasion force would eventually need something in the order of 1 million gallons of fuel a day, and that figure would only grow as more divisions came ashore and pushed further inland. The obvious answer, and the one every previous amphibious campaign had relied upon, was to bring the fuel in by tanker and unload it at a captured port. There was just one difficulty with that plan. The Germans knew it too. Every harbor along the French coast that might have taken a tanker had been fortified, mined, and prepared for demolition. The planners had already seen, in the disastrous raid on Dieppe 2 years earlier, exactly how costly an attempt to seize a working port could be. Even if the Allies did take a port intact, the enemy had every intention of wrecking its cranes, its jetties, and its fuel storage before withdrawing, a lesson that would be proven brutally correct when Cherbourg finally fell in June 1944 to find its harbor facilities systematically demolished. There was a second option, no less fraught. Tankers standing offshore, pumping fuel through hoses onto the beaches themselves, then distributing it by drum and jerry-can. This had obvious appeal in its simplicity, but the channel is not a swimming pool. A storm could scatter a fleet of tankers in hours, and a beach littered with fuel drums was an inviting target for enemy bombers, a single incendiary round turning a supply dump into an inferno. Worse, the entire scheme depended on ships making the crossing again and again, ships that were desperately needed elsewhere, through waters patrolled by U-boats and E-boats and seeded with mines. Every gallon that reached Normandy this way would have to run a gauntlet over and over for as long as the campaign lasted. The scale of the shipping problem alone was daunting enough to give planners sleepless nights. Britain in 1944 was an island groaning under the weight of a war that had already consumed vast quantities of merchant tonnage to German submarines, and every tanker diverted to ferrying petrol back and forth across 20 or 30 miles of open water was a tanker that could not be carrying ammunition, replacement vehicles, or the thousands of tons of other supplies an advancing army required. Planners also had to reckon with the notorious unpredictability of channel weather. The same storm that, in June 1944, would go on to wreck one of the 2 artificial mulberry harbors built to support the landings was a stark reminder of just how quickly the sea could turn from an asset into an enemy of its own. A fuel supply that depended entirely on calm water and undamaged ships was, by definition, a fragile one, and fragility was precisely what an invasion of this scale could not afford. What the planners needed was something that had never existed before, a way of moving fuel across open sea without a single ship making the crossing more than once, a supply line that a U-boat could not sink, a spotter aircraft could not see, and a coastal battery could not shell. It needed to be laid quickly under wartime conditions, using technology that existed in 1943 rather than technology someone hoped might exist by 1946. On paper, it sounded close to impossible. The channel bed is uneven, subject to strong tidal currents and in places more than 60 meters deep. No one had ever laid a pipeline capable of carrying petrol rather than a mere telegraph signal across such a distance under such conditions in wartime. The answer came from an unlikely marriage of two industries that, on the surface, had nothing to do with one another: the oil business and the submarine telegraph cable business. The chief figure behind the project was Arthur Hartley, chief engineer of the Anglo-Iranian Oil Company, working alongside the cable manufacturers Siemens Brothers and the Institution of Petroleum. Between them, they devised a pipe that borrowed its manufacturing technique almost wholesale from the undersea telegraph cables that had linked continents since the Victorian era. Instead of copper wire at its core, though, this cable-like pipe had a hollow lead lining roughly 7.5 centimeters across, wrapped in layers of paper insulation, steel tape, and tarred hessian for protection against the corrosive assault of seawater. The design became known, from the names of the men and companies behind it, as HAIS pipe, and it could be made flexible enough to bend and coil, yet strong enough to carry petrol under pressure across the seabed. The genius of borrowing cable-laying technology was that the manufacturing infrastructure already existed. HAIS pipe could be produced in continuous lengths at cable works on the Thames and the Medway, then wound onto colossal floating drums built specifically for the purpose. These drums, more than 18 meters across and weighing in the region of hundreds of tons, were given the deliberately unglamorous nickname of conundrums, a play on the word conundrum that stuck instantly with the men who built and towed them. Each conundrum could hold around 70 or 80 kilometers of pipe, wound around a floating spool not unlike an enormous cotton reel, and the whole assembly could be towed across the channel by tugs, the pipe paying out from the drum as it went, in much the same way telegraph engineers had strung wire between continents decades before. Building a conundrum was itself an engineering feat rarely given the credit it deserves. Shipwrights had to construct a drum capable of floating while carrying a load of pipe heavier than a small warship, keeping it stable enough in open water that it would not capsize or break apart under tow, all while the pipe itself paid out smoothly under tension rather than snagging, kinking, or snapping under its own weight. The men who built the conundrums worked largely at sites along the Thames estuary, drawing on the skills of shipyard workers more accustomed to building tankers and destroyers than colossal floating cable spools, and the entire construction program had to be carried out under the same blanket of secrecy that shrouded every other part of the project. Workers on the conundrum program were often told only what they needed to know to complete their particular task, a security measure that meant very few people involved understood the full shape of what they were building until long after the war had ended. The pipe itself, when examined closely, was a marvel of layered protection. At its core ran the hollow lead tube that actually carried the petrol, chosen because lead could be extruded into a continuous seamless tube of enormous length, a technique cable manufacturers had already perfected for insulating telegraph wire. Around this core were wrapped layers of paper impregnated with petroleum jelly, providing both insulation and a degree of flexibility, followed by a sheath of steel tape wound in a helix for strength, and finally an outer layer of tarred hessian and steel wire armoring to protect the whole assembly from abrasion against rocks, sand, and the anchors and propellers of passing shipping. The finished pipe could be coiled almost as readily as rope, a property essential to the entire scheme, since a rigid pipe of similar length could never have been wound onto a drum for towing in the first place. A second, entirely different system was developed alongside HAIS pipe, this one using rigid steel pipe instead of flexible cable-style pipe. Steel pipe could carry fuel at higher pressure and last longer, but it could not simply be coiled onto a drum. Instead, engineers devised a scheme where lengths of steel pipe were welded together on board specially adapted vessels, and then reeled out directly from a giant floating drum mounted on the ship itself, a system that came to be called tombola. Picture something like a colossal fishing reel mounted on the deck of a ship, paying out rigid pipe rather than fine line, and you have the essential idea. Both systems, HAIS and tombola, were developed in parallel, tested extensively in British coastal waters, including trial layings across the Bristol Channel, and refined again and again before anyone dared attempt the real crossing. The scale of what was being attempted only becomes clear when you set it against something familiar. A single length of HAIS pipe, fully wound onto its conundrum, weighed roughly as much as a fully loaded goods train, yet it had to be handled with a delicacy closer to threading a needle, because a single kink or crush in the pipe wall could render an entire multi-kilometer length useless. The pumping stations built to drive fuel through these lines, disguised on the English side behind the fronts of seaside cottages, ice cream parlors, and even a garage, were designed to look, from the air, like anything but what they were. One such installation on the Isle of Wight was built behind a mocked-up bungalow. On the French side, similarly disguised stations were established once the beachhead was secure enough to receive them. The operational history of Pluto began in earnest shortly after D-Day, though the first serious cross-channel line, laid from Sandown on the Isle of Wight toward Cherbourg in August 1944, suffered repeated failures as the pipe struggled against strong currents and an uneven seabed. It was, in truth, something of a disappointment in its earliest form, delivering only a trickle of the fuel that had been hoped for. Engineers found that the seabed between the Isle of Wight and Cherbourg was far less accommodating than trial runs closer to home had suggested, with stretches of rock and shifting sand that put unexpected strain on lengths of pipe never designed to be dragged or flexed against an uneven surface for any length of time. Several of the earliest Cherbourg lines failed within days or weeks of being laid, a sobering reminder to everyone involved that a scheme which had worked perfectly in trials across the calmer waters of the Bristol Channel could still come unstuck when tested against the reality of the open sea. The engineers did not abandon the concept, they refined it. A shorter and altogether more successful crossing was established between Dungeness in Kent and Boulogne, then further on towards Calais and the front lines beyond, once those French ports had been secured by advancing Allied forces in the fine autumn of 1944. This shorter route, across a narrower and calmer stretch of water, proved far more reliable, and here Pluto at last began to deliver on its promise. The code names given to these various lines, Bambi and Dumbo among them for the Dungeness routes, hardly hinted at the seriousness of the enterprise, but such incongruous naming was itself a form of security, an ordinary-sounding word attracting far less attention in a signal or a memorandum than anything resembling secret channel fuel pipeline would have done. If you are finding this interesting, a quick subscribe helps more than you know, because there is a great deal more still to uncover about the pipeline the Germans never found. By the war's final months, a network of Pluto lines, numbering more than 20 separate pipes in total across both the Cherbourg and Dungeness routes, was feeding fuel directly into the Allied advance across northern France, into Belgium, and eventually toward the German border itself. Precise wartime output figures remain difficult to pin down with total confidence, since some records were classified for years afterwards, and others were simply never kept with the rigor historians might wish for, but reasonable estimates place the total fuel delivered through the Pluto system, by the time of the German surrender, somewhere in the range of hundreds of millions of liters, a contribution that supplemented, rather than replaced, the fuel still being brought ashore by tanker and drum, but freed enormous shipping capacity for other purposes at a moment when every vessel afloat was needed elsewhere. It is worth pausing on the comparison with what the Germans themselves attempted, because there is a natural instinct to assume that a nation famous for its engineering must have had something similar. They did not. German planners had, in fact, considered underwater fuel lines for their own aborted invasion of Britain in 1940, Operation Sea Lion. But the concept never advanced past preliminary study, partly because the invasion itself was shelved and partly because Germany's undersea cable industry, while competent, had never been pushed to develop flexible fuel-carrying pipe on anything like the scale Britain achieved. Instead, German logisticians relied overwhelmingly on rail and road transport to move fuel toward the front, a system that worked reasonably well while supply lines remained short, but which grew steadily more vulnerable as Allied air power targeted marshalling yards, bridges, and fuel depots with increasing precision through 1944. There was no German equivalent capable of moving fuel across open water without a single vessel ever making the crossing, and no evidence that any such scheme was seriously pursued once the war turned decisively against Germany on the Western Front. The Americans, for their part, contributed engineering expertise and some of the pumping equipment used at the receiving end, and later would draw on Pluto's lessons for their own post-war undersea pipeline work. But the flexible HAIS cable pipe technique in particular was a distinctly British innovation, born from that unlikely fusion of oil engineers and cable manufacturers. American logistics in Normandy instead leaned heavily on an ambitious overland fuel pipeline system built across France itself once the breakout from the beachhead was underway, moving petrol inland from captured coastal terminals by pipe and rail rather than relying on a cross-channel undersea link in the way the British scheme did. Both approaches solved the same underlying problem of moving fuel efficiently to a rapidly advancing front, but only the British scheme attempted, and ultimately succeeded in, laying pipe across the seabed of open water on this scale. Nothing built by any other combatant nation during the war matched Pluto for the sheer audacity of running a fuel supply beneath a heavily patrolled stretch of sea. The legacy of Pluto is a curious one, because its practical contribution to the campaign, while real, was smaller in absolute terms than the fuel brought ashore by more conventional means, and for years afterwards some historians debated whether the enormous effort of designing, manufacturing, and laying the pipeline had been worth it against what more straightforward tanker operations might have achieved regardless. The Cherbourg lines, in particular, never came close to matching their intended output, and some historians have argued that the resources poured into research, manufacturing, and the elaborate secrecy surrounding the project might have yielded more immediate benefit if directed elsewhere. Others counter that the shipping capacity freed up by even a partially successful pipeline, at a moment when every hull afloat was desperately needed for troops, ammunition, and equipment, more than justified the investment, and that the more reliable Dungeness to Calais route in particular delivered fuel steadily and safely for many months during the advance into the Low Countries and towards Germany. What is not in dispute is the audacity of the concept and the quality of the engineering behind it. Pluto proved, for the first time, that a nation at war could run a continuous fuel supply across open sea without ships making repeated crossings, a principle that would go on to influence civilian undersea pipeline engineering for decades, including the offshore oil and gas pipelines that today snake across seabeds around the world, carrying products from fields far out at sea back to onshore refineries. The psychological value of the scheme, too, should not be understated, quite apart from the fuel it delivered. Knowing that a secure, largely weatherproof fuel supply existed beneath the channel gave planners a confidence in sustaining the advance that tanker convoys alone could never have provided, freeing commanders to plan operations without constant anxiety over whether the next fuel delivery would arrive on schedule or at all. Sections of original Pluto pipe survive and can still be seen today, notably at the Pluto Museum near Sandown on the Isle of Wight, close to where that first troubled Cherbourg line began its journey, as well as at the D-Day Story Museum in Portsmouth, tangible remnants of a scheme that once had to remain entirely invisible to succeed. Return, for a moment, to that dark channel crossing in August 1944, the conundrum turning slowly in the water, the pipe paying out unseen beneath the waves. No German patrol boat ever intercepted a Pluto crossing. No Luftwaffe reconnaissance photograph ever revealed what those disguised pumping stations on the English coast were truly for. An entire logistics operation, built to sustain the advance of armies across a continent, was constructed and operated for months, without the enemy ever fully grasping that it existed at all. That, in the end, is the real achievement of Pluto, not simply the ingenuity of bending cable-laying technology to an entirely new purpose, though that alone would be remarkable, and not simply the sheer scale of pipe manufactured and laid in a matter of months, though that too is extraordinary, but the fact that a vast, continuous, industrial-scale operation ran beneath the waves of one of the busiest and most heavily watched stretches of water on Earth, and the enemy never knew. Hitler's coastal defenses were built to stop an invasion fleet. They were built to repel tanks and landing craft and paratroopers. They were never built to stop a pipe. And in the end, it was the thing nobody was watching for, laid quietly in the dark, that helped keep an army moving all the way to Germany's door.